how can we solve this complex homework problem? So this is called the ladder problem, and how can we apply ideas that we've learned about in class from static equilibrium to solve this problem? Here's the problem. We've got a ladder, and this ladder is leaned up against the wall. So here's the ladder, side view of it, and then it's leaned up against the wall, and there's a part of it that's against the ground like here, and we've got an angle of inclination of theta. And right here where the ladder touches the ground, there's some friction. And because of that friction, we can quantify it using this coefficient of static friction. So the question is this: how far out can we lean the ladder? Can I lean the ladder out like this, or can I lean it out like this? How big can I make that angle before it starts to slip? And you might guess that if I'm leaning the ladder way out like that, it's basically going to start to slip. So what's the minimum angle I can use to keep this ladder in place given a coefficient of friction of mu s? The ladder's got a length of L and it's got a mass of m. So let's see if we can solve this thing. Now remember, in static equilibrium, we have the following equations. The sum of the forces in x have to equal 0. The sum of the forces in y have to equal 0. And the sum of the torques have to equal 0. So let's start to think about applying one of these equations. And the way we're going to do that is I'm going to first start drawing some forces. Okay? So right about in the middle of the ladder, we're going to have the weight pulling down. We'll call that mg. And pushing up from the ground is going to be some force. We'll call it the normal force, like that. And now I can take these two forces and realize that they're both acting in the y direction, and that'll be relevant for the middle equation down below. There's another force that's acting here. When the ladder is leaning against the wall can push out in a manner that's perpendicular to the wall. We'll call that the force of the wall, like that. Okay, so let me draw these forces down here. We've got something going up like that. We've got something going down like that. And then in the x direction, we've got something going like this. Now you can imagine that in the y direction, these two forces are going to cancel to provide static equilibrium. But here in the x direction, we don't have that. We've only got one force going that way. So we must be missing a force. What we need to have is another force that's going like that. Where can that come from? Well, that's where the friction comes in. I can have a force like that, the force of friction going in that direction. So these are going to be all the four forces on the ladder. And now we want to write equations to work these guys out. So let's do it. In the x direction, we're going to have this. The force of friction will be positive, and the force of the wall will be acting in a negative direction, and the sum of them must equal 0. So that's a valid equation in the x coordinates. In the y coordinates, we're going to have this. We're going to have the normal force going up, and we're going to have mg going down. And that has to equal 0. So for right now, we're going to hold off on the torque, and we'll just look at these equations. We got that one, and we've got this one. Now I can simplify it a little bit further. I can say the force of friction basically equals the force of the wall, and the force of friction from what we learned before should be mu static times the normal force. That's how friction is defined, equals the force of the wall. So we'll use this, that's been worked a little bit more, and then to develop this one in y, I can basically say the normal force is equal to mg. It's got to be true. And so I should be able to then plug in this normal force here into this equation here. And if I do that, then I get mu static times mg equals the force of the wall. All right. So actually, the equations that I'm going to use are going to be this equation here, and we'll use this equation here. What we haven't done yet, as I mentioned, is this sums of the torque type of thing. So let's do a diagram of that on the next page here. So let's go in. So the ladder roughly looks like this. We get a force coming up here. We get another force going here. This is the force of friction. This is the normal force here. I've got the force from the wall acting like that, and I've got mg right in the middle of the ladder pulling down like that. Now I want to look at the sum of the torques equal to 0. And I want to pick a pivot point in this object. I could pick here, I could pick here, or I could pick there. I want to pick one of these points and sum the torques all around them. And the point that you pick really matters here. So if I pick a particular point like this one down here, whoops, keep doing that, go back. So if I pick a point like this one down here, what happens is when I write the torque equation, this force doesn't have any effect of twisting things around this point. And this force doesn't have any effect of twisting it either. It's only this force, which is going to rotate things that way, or this force, which is going to rotate things that way. Those are the only forces that are going to exert any torque. So if I pick the point to sum the torques over right here, then I don't need to fit into my equation the normal force or the force of friction. That's going to be a plus, okay? So I'm going to try to pick that. Now, the other thing I have to do is I have to make sure that the components of the forces that I'm going to be looking at are perpendicular. So I want the perpendicular or 90-degree angle component of the force here. This is the force from the wall. It's got to be 90 degrees from the ladder. And I also need the weight, the mg, I need to pick this component 90 degrees from the ladder. So let's draw those guys in and try to identify how we can do a little geometry to see this better. Let me make this slightly bigger. And this way we'll be able to see what's going on. So here, let's pick a slightly different color. What I want is a component of this force. This is the force from the wall that goes out like this, and then there's another component of it that goes that way. And I'm also going to resolve this guy. This is the force of mg into components that go like this. Again, what I want is I want the perpendicular component, this one here, and I want this one here. And I've got to use the geometry of the situation to figure out what these angles are. What we know from before is that the angles are, I want black. Where did I go? Let me go back to the black right there. Okay, so what I want to do is draw this angle down here. That's theta, like that. So that's angle theta. And what I want to know is how is that related to some of these other angles? So what I can realize is that this angle here must be theta, because this line here and this line here are parallel. And so these angles must be the same. This theta here and this theta down here. So I've got theta there. All right, that's good. So if I've got theta there, then what that means is that if I go back, boy, I'm colorblind, so I'm going to have real trouble here picking a color. Okay, I'll just pick that one. So what I'm going to do is I'm going to say this component here is then the force of the wall times the sine of theta. Why is that? That's because this component is the sine of this angle theta, right like that. I could also draw these components like this. I could draw it like this, and that's another, this line will be exactly the same as this line. So that's the force of weight times the sine of theta. All right, now, what about this guy down here? This is going to be mg, that's the force of the hypotenuse of this triangle, times some angle, and let me draw the little angle here. This angle, let's call it alpha, okay? So it's going to be mg times sine of alpha, like that. Now, how do I know what alpha is? And this is where it gets a little bit tricky. And let me draw a little triangle here. We've got to do some trigonometry. So we've got this triangle with these dashed lines, right like this. I'm going to draw this triangle here again. Looks like this. We've got the angle theta here. We've got this angle alpha, and we know that this is 90 degrees. So that is this triangle that I'm drawing right here. Okay? What I know about this triangle is that 90 degrees plus theta plus alpha should all equal 180, because the sum of the angles in a triangle are 180. So if I subtract 90 from each side, I get 90 degrees equals theta plus alpha. I get alpha equals 90 degrees minus theta. So that's what alpha is. So I can now go in and write my torque equation. So I've got one torque that's basically moving things in that direction. I've got another torque that's rotating things in the opposite direction, like that. So this upper one, from the force of the wall, that's going to rotate things counterclockwise. So it's going to be a positive torque. So the sum of the torques equals 0 equal the force of the wall times sine theta. But I also have this force down here, all right? Oh, by the way, this thing is at distance L. So maybe I should erase this and just make it a little bit more clear. L. Okay, so L, that's the length of this here. And for this other force, the component of the weight that's acting perpendicular, that's a distance L divided by 2 away, okay? And that's operating in the clockwise direction, which means that it's going to be negative. So it's going to be negative L over 2 times mg sine of alpha. So that's my torque equation. Now I'm going to elaborate that a little bit more down here. Let me make things more clear. This term here of sine alpha, as we said, it's really the same thing as sine of 90 degrees minus theta. And really that's going to be the same as cosine of theta, like that. This is one of your trig understandings that you should have gotten from earlier. So now what I can do is I can rewrite this torque equation differently. I can basically say the sum of the torques equals 0. And so that's going to equal plus L, force of the wall, times sine theta, minus mg times cosine theta, like that. All right, and if that all equals 0, then I can basically say L times the force of the wall times sine theta equals mg times cosine theta. And if I want to work this a little bit, oh yeah, and this thing I forgot has L over 2. I didn't copy that down. L over 2, L over 2, like that. Because that's the length of the distance to the pivot point. That's the length of the distance to the pivot point. Now I can cancel things. Let me go back to my black marker here. I can cancel this L with that L. And I can rewrite this in terms of, go back to that. I can now say the force of weight times sine theta equals mg times cosine theta. Oh, sorry, force of the wall. I can say the force of the wall is going to equal mg cosine theta divided by sine theta, like that. And I've got a 2 here as well, still like that. And this ends up being the force of the wall equals mg over 2 times tangent of theta. Because sine over cosine is tangent, but cosine over sine is 1 over tangent. So I've got this equation here for the force of the wall, and I've also got this one here for the force of the wall. So let me take that one down and see if I can bring these guys together. So the force of the wall is mu s times mg. So the force of the wall is also mu s times mg. So now I can substitute this one into there. I can basically take this term and substitute it in. So I can have something like this. Mu s times mg equals mg all over 2 times tangent of theta. Cancel the mg's like that. And then I can basically get something like this. If I multiply both sides by tangent theta, I get tangent theta like that equals 1 over 2 times mu s. And if I take the arctangent of theta, or arctangent of 1 over 2 mu static, that should give me the angle. So this is the answer right here. And as long as the angle is like this and doesn't get smaller, then the ladder won't slip. The ladder will not slip as long as that angle doesn't get smaller than that. So I want a big angle. In other words, I want the ladder pretty close to the height of the wall. But if I start to tilt it more like that, where theta becomes bigger and bigger, it's going to slip. So my minimum angle is something given by this equation here. This is how you combine the sum of the forces in x and y with the sum of the forces in torque with multiple equations where you have to kind of bring them together and solve for one variable. I hope this has been helpful. Let me know with any comments or suggestions about how I can improve or what you think. Thanks for listening.